the squeeze theorem, which is truly a really cool math theorem. And it's a really good example of how mathematicians kind of trick things the way that they want to get the answers that they want, basically. So it's kind of interesting, but the idea here is if we have like this red curve, let's just say we need to approximate the limit of it when x is approaching a, and we can't for some reason. We can't approximate it algebraically. So, but however, we're able to create a function that we know that's always greater than this function. That's always greater than the red graph. And another function that we know is less, or at least within a local area, we know that it's less than the graph. And then if we know that the graph of both of those two, the upper function and the lower function, and it's why it's called the squeeze theorem, if they both equal the same limit at that spot of A, then this red graph has to be pushed right in between them, would have to be that exact same value. So it kind of closes that gap. It squeezes it and compresses it together. So in order for this to work, our function g of x is basically what we're going to be using here. We need an upper function h of x that we know is greater than g of x on some interval. It doesn't always have to be greater. It has to be within that local area. And we need a lower function like f of x, something that we know is less than. And we also need to know that the limit of f and h, the lower and the higher function, that they approach the same value at that spot. If they're approaching that same value at that spot, then g of x must also be that same value because it's compressed right in between them within that local interval. Really cool theorem, like I said, and it really just gives you this way. I wish we actually really did it in Con because there's some trig and stuff, bounces up and down, and we're able to compress it knowing that sine is less than 1 and greater than -1, and we're able to kind of put it in this situation, but we're not going to actually do that. We're just going to take this main concept right now and take a look at these problems. And you can see, like I was saying, they use a lot of trig. So to prove this limit equals 1, so they want to prove that this limit equals 1, Charlie suggests to use negative absolute value of x plus 1 and absolute value of x plus 1 in order to approximate, or in order to apply the squeeze theorem. So once again, we're just judging what other people are doing for the squeeze theorem. We don't have to actually come up with the functions. That's kind of the cool part when you do have to come up with the functions. But it takes a lot of thinking because you're probably thinking, how did Charlie even come up with that? Once again, they're going to come up with it for us. We're just going to figure out, hey, is one of them greater, is one less than, and are they approaching that same limit? We're basically seeing if this applies to it. So looking at this, you can see this pink graph here, h of x is always above, at least within this local region when x is approaching 0. Within this region, it's always above the blue graph, and then the orange one is always below it. And then notice that it's being squeezed right there at that spot of 0. It's compressed. They both equal the same limit of 1 at that spot. So I would say this is an appropriate use. Charlie's good. So let's look at whenever this can go wrong. So here we go, same graph here. And they're going to use, this time, Anish is going to use x cubed plus 1 and negative x cubed plus 1. But take a look at this graph. This pink graph here is not always greater than the blue graph within that local area because look, it does this little switch right there. It's greater for the left of that spot, but the right, we need a little bit on the right-hand side to be greater as well, and it's not. Same thing with the orange. Look at it. It's below it, and then it goes above it. We want it to stay below it, at least within this local area. So no, it's not correct. I think it's this one right here because look, what the output of one of the functions always is, it's not true that the output of one of the functions is always below f. Because look, this one's not always below f because it's greater than it, at least within that interval, within that area. And then for the last reason right here, you can see this graph, and we won't go too much into the details here. This one's always above it. That's good. This one's always below it. But look, is this really squeezing it to that spot of 1? No, it's not, because the limit for this orange graph for g is not 1 at that spot. So that means that this blue graph, for all we know, could be doing like this, and it wouldn't actually truly approach 1. We need this orange graph to go up to 1 to compress that blue graph within it. So that's going to be the last reason. No, Brenda's suggestion is incorrect because it's not true that the limits of g and h are both equal to 1. So once again, this is a really cool theorem here. I wish we could spend more time with it, but this is all we're going to do with it. If you have any more questions on it or you really want to learn more about it, I can get you more material on that. Just let me know. But that's pretty much it. We just want to take a look and see if there's a function that's greater than it within that area, less than it within that area, and then from there, they both need to approach that same value, and that's what compresses, that's what squeezes it into that little spot that